Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a great pleasure to introduce Emery Berger, an associate professor at the University of Massachusetts in Amherst. Emery got his PhD in 2002 from the University of Texas, and I've been working with him since then on a number of different projects. I have to say, Emery always surprises me by the creativity of his work, and also by the fact that he takes ideas that you think are just out of this world, and he makes them work in practice. So I think this is another example of that work. And today, Emery's going to talk about parallel programming in Grace.
Thanks, Ben. Hi, everybody. All right, so you see the title of the talk, Grace, Safe Multi-Threaded Programming for C and C++. But what I want to talk about first is garbage collection. So this may seem a little surprising. Garbage collection is a topic that obviously, well, I'm not sure if it's near and dear to my heart, but at least it was at one time. But it's a well-established technology. It's something that it now works, right? So here's the world's best garbage collector, Wall-E. He never stops. There's always garbage to be found. And the idea of garbage collection, at least the idea for Wall-E, is you've got a robot, and the robot is going to find your garbage and take care of it. And in a garbage-collected language, right, the runtime takes care of your memory errors. And this is great. You can deposit your garbage wherever you feel. And the runtime will go after it and clean it up. This is actually, so that's Hans Bohm, by the way, for you who don't recognize him. This is especially suitable here. So Hans built this conservative garbage collector for C that you all may have heard of. And really, it's exactly what I'm getting at, which is it's garbage collection that is intended to deal with programmer errors. So you're in the world of C. You make some mistake in your memory management. You throw Hans at the problem, and the problem goes away. All right, Hans E. Right. So the result of all of this work on garbage collection is it's a success story, right? There are now plenty of languages where garbage collection is now practically taken for granted. And for many, many years, it was considered very controversial. Who would ever adopt it? And now you can barely think of. I think there are no dynamic scripting languages, for example, that don't have garbage collection. JavaScript, of course, Python, Perl, Ruby, not to mention Java and C#. It only took 35 years. I guess if you're patient like Wall-E, then all good things come to those who wait. OK, so wouldn't it be nice if someday we could have garbage collection for concurrency? So this is sort of the vision of this talk. I would like to be in a world where I can take my program that has all kinds of bugs, right? I just throw, I write a concurrent program with just as many bugs as I want. I leave off locks. It's full of races. And then Wall-E comes and will clean up after me. I think that would be great. So I just want you to think of the rest of this talk through this, this sort of view of garbage collection for concurrency. All right? OK. The one question that immediately comes to mind, though, is, wait a second. What does that even mean? What would it mean to garbage collect concurrency errors? We know what it means to garbage collect memory errors. Concurrency, it's not so clear. OK. So a lot of this is not going to be new, but we'll go through it anyway. In the beginning, there was the core. The core was good. And every year, the core got faster and faster. Life was wonderful. And so if you wanted to write a sequential program, right, you just write your sequential program. Every year, it got faster and faster. You just write a very simple program. You're not meant to understand this, but it's just a very, very simple loop. And it was great until one day, things got a little too hot. And now we're out of luck, right? It leveled off. And so then they said, oh, wait, we know how to build the one core. What if we give you 4? And we said, we don't want 4. And they said, sorry, you're getting 4. So now we have 4 cores. And the promise, of course, is, well, if you give me more cores, then I can run faster, because I can do more things at once, right? The last little stripe has to lag along, Amdahl's law. All right, so that's great. And if we could do this, if we could parallelize all our programs, right, it would be as if Moore's law never stop. Now, I'm being a little loose and fast with what Moore's law means, but you all get the idea. OK. The problem, of course, is anybody in this room knows who has programmed concurrent programs. How many of you have written concurrent programs? OK. How many of you have written concurrent programs that have bugs? OK. All right. Don is like, what? Bug? Me? So here's the kind of problem you get, right? You run the program once. It works fine. You run it again. Something else happens. Sometimes it works. Sometimes it doesn't. Right? So these are races, of course. And if you look at this code, you can see that there's indeed a race. If you imagine this being multi-threaded down in this loop down here, if this was a parallel 4, the problem is that these are races, right? Color and row and drawbox are being done. Really need locks around them. So if you then throw locks around the updates to color and row, you would think everything would work. And it will prevent races. But unfortunately, sometimes you get this or this, which is rather surprising. And so these are atomicity violations. So here the problem is you put locks around things, but you made them too fine-grained. You really wanted to draw this whole rectangle in a color and then do the next one, not change the color while you're drawing the row. So you need to move the lock up. And for those of you who like transactional memory, pretend that lock and unlock means atomic and curly braces. All right, same thing. And I should observe in passing, transactional memory does not solve any of these problems, right? It's really a question of where you put these braces. So if you make a mistake and you would put them where they were here, you would have exactly the same problem. You need to put the braces in the right place. And transactional memory does not deal with this problem, right? You still relies on the programmer to get it right. OK, so here's another kind of problem. So the one thing transactional memory does deal with, which is deadlock. Unfortunately, sometimes it converts it to live lock, which is far, far worse. But we won't get into that. OK, so here's another weird error. If you see this, here's the flag 1, flag 2. So this is what's called an order violation. This is a recently identified concurrency error, which I think is great. Good. New errors. Fabulous. So the new error is programmers who wrote this code assumed that when you spawned a thread, that thread would be delayed, that it wouldn't just spawn immediately. And so they then did some other stuff right after they spawned the thread. And almost all the time, that other stuff preceded the actual execution of the next thread. But then they changed versions of the OS, and the scheduler changed. All of a sudden, the thread started executing first, and weird things happened. So fun concurrency errors. So to recap, back in the day when we had the one core, it was great. Everything was sequential. No bugs, right? Remember? All right. It was maybe easier, OK? It was a world of unicorns and rainbows. Cooperatively. So now we have races, atomicity violations, deadlock, order violations. So this is concurrency hell. So it's a bad situation. So what we'd like to be able to do is to come up with a world that takes us back to those unicorns and rainbows to some extent. And so the object of grace, which is what I'm going to talk about today, which is you can view as a sort of garbage collector for concurrency, is intended to get rid of all of these errors, okay, and impose sequential semantics. So you'll take your multi-threaded program, and it will run as if you had written a sequential program. Okay? So I'll explain what that all means in some detail. The idea behind Grace, however, it's not a new compiler. It's a runtime solution. Roughly speaking, to use Grace, you swap out the pthreads library for the Grace library. And you don't need to make any other changes to your code. Okay? This guarantees sequential semantics, gets rid of these errors, and I'll show you how you can actually get some performance out. Yes?
What do you mean by sequential semantics? Code contains spawn thread. I mean, there is no sequential.
Yeah, that's exactly the next thing, right? So in the rest of the talk, the very first thing I'm going to talk about is going to address that question, which is what the hell do I mean? Right? I've got multi-threaded programs that are going to run on multiple cores, and now I'm saying they're sequential. What do I mean by that? I'll talk a little bit about what goes on inside, right? What's under the hood, and then present some results. Okay? All right, so to the first question. So for the purposes of this talk, I'm going to use the syntax of the Silk programming language. For those of you who are unfamiliar, this is a C-like programming language that is extended with spawn, which is the moral equivalent of pthread create, and sync, which is the moral equivalent of pthread join for all of the preceding children. Syntactically, it's just cleaner and it makes the examples easier. But Grace actually implements the pthreads API. Okay? Here is a little program that says spawn a thread to run the function f of x and store the result in T1. Same thing with g of y and T2. And sync means wait for both of those threads to complete. Okay? Very simple multi-threaded program. So the execution looks something like this. You say spawn f of x starts executing. It runs concurrently with the main program, which now spawns g. Now everything is running concurrently until they hit sync, and sync is like a barrier. Okay? All right, so that's your concurrent program. So what I want to do is I want to take this concurrent program, and I want to impose an order on the execution. What I'm going to impose in particular is a left to first, depth first ordering. Left to right, I mean, depth first ordering. But what that corresponds to is actually much easier to explain syntactically. All we do is we get rid of the keywords spawn and silk. So this is sort of an elision of all of the concurrency operatives in the code, and you're left with a sequential program. So where you had a function call before that was supposed to be spawned asynchronously in another thread, now it's going to be executed synchronously. So f of x will be executed to completion, then g of y. So these are the semantics that Grace is going to provide. Okay? It's not really going to execute them this way, because that would defeat the whole purpose of having multiple threads from multiple cores. Okay? Yes?
So you chose that there's certain parallel programs that you're simply not going to run.
That's exactly right. So first let me say what this does, what the implications are, and then I'll talk about the limitations. And you're absolutely right. So first, it should be clear that most of these problems go away, right? As soon as you move into a sequential world, these sort of concurrency errors, by definition, stop really mattering. So a race doesn't matter if threads aren't running in concurrency. Same thing with atomicity violations. We don't need locks anymore because there aren't multiple threads, so that gets rid of deadlock. And there's no order violations. The order is fixed. It's program order. Okay? However, there are some limitations. If you have threads that are intended to execute forever, so some sort of a reactive thread. So if f of x and g of y, when you spawned them, they were both supposed to run forever. Now we compose them, and f runs forever and g never runs. You have a bit of a problem. So you can't have infinite thread execution. The other thing, which is perhaps a more crucial limitation, is they can't communicate either. Okay? They can communicate in the sense that the effects of one thread become visible to the next thread or to a child thread, but they can't use condition variables. So in fact, in Grace, condition variables are not exposed in the library. If you try to link with the Grace library and you have condition variable calls, it'll complain at compile time. All right? So this sort of communication is ruled out. Okay?
And of course, I can't implement my own using shared memory.
You can't
implement my own channels using shared memory, then that would be also dead.
I mean, there's...
And condition variables and...
You can't implement, I mean, any sort of thing that does that, there's no way to actually implement it in Grace. Right? You're prevented from doing so. And the primitives aren't exposed. Okay?
ASM section.
Oh, well, I mean, okay, I see. So you want to violate the boundaries, right? Yeah, okay, sure. Yes, that's right. There are certain evil things you could do to try to get past this. And then, if you roll your own or you include something that's not called pthread cond whatever, it's called, Manuel cond, then Grace doesn't know about it and it will not behave as you would like. Okay? What it's intended for is for forkjoin parallel code. So the whole object of writing these parallel programs ostensibly is to take advantage of all of these cores and take computations that were sequential and make them run faster. And forkjoin is a popular paradigm that makes it fairly easy. It's a nice, easy abstraction to think about how you break things up, break something into pieces, maybe even have nested forkjoin. That all works. And so there's a bunch of different libraries that exploit exactly this, provide this sort of API. So MapReduce is a forkjoin framework. Silk is this programming language I described earlier. Intel's thread building blocks library. I should add, Java also has a new forkjoin library that's coming out, again, to just enable programmers to use this paradigm. OK. So let's see. So what's going on? How is it possible for me to take a code that used to run sequentially and, as I'll tell you later, get any performance out of it? So magic. Not much of an answer. There are two pieces here, two crucial pieces. One is some magic, which is really you could think of as hackery. And the other is ordering. So we need ordering, and we need this hackery to make this work. So first, I'll talk about the hackery. So this is going to sound terrifyingly evil or awesomely clever. You decide, OK? So here's what we do first. So we take these threads. You've got this program, and it spawns threads. We're going to turn this program that was written using threads into a program that uses forks. That is Unix-level process creation. All right? So you may be thinking to yourself, dear God, why would you do this? But it will become clear in a minute. And I should add, right now, this is implemented in Linux. Fork is actually quite efficient. In fact, thread creation uses the exact same code base as fork. So the difference in terms of performance, as you'll see, is not really a material problem. What we do this for, actually, is to provide isolation. So the great thing about processes is processes have separate address spaces. So what I can do is I can run one thread and run another thread, and all of their local effects are isolated from each other. So we're going to use this to enable speculation. And that's how we're going to get performance. So for example, I can start running f of x, and I can then run g of x completely in parallel. And if one of them does something that would violate this sequential ordering, I can always throw away its results and execute it again. So in the worst case, I'll end up with a sequential execution. I will hopefully not be in that case, and I'll get some parallelism out. All right? So, and it turns out nested threads are OK. I'm not going to explain the details here. But you may be asking yourself, wait a minute. These are in separate address spaces. Well, you should be asking yourself this. They're in separate address spaces. F does something, G does something. But they're totally separate processes, right? They can't see the results of what they did. It doesn't make any sense. So what we do is we actually use low-level memory mapping primitive to basically expose the shared space. And then each guy has a private copy of the same mmap region. So this is something you can do with mmap. When you go and you write to one of these pages, it's copy on write. So everybody will end up with their local versions of the heap, and they can always see, say, the heap and the globals that had been committed before. So it's a way of giving you thread-like convenience in terms of having shared memory, but still get isolation. Now, when these threads are running, like I said, they're running in isolation. They get all their private versions. Eventually, this memory has to be shared, right? So all the threads need to be able to see all the results of preceding threads. So what we do is we impose ordering on how their results are committed. So there's no ordering of the execution. The execution runs completely in parallel. But f of x precedes g of y in program order. And this is the sequentiality we want to observe. So f of x's results need to happen first, logically, then g of y's. So what we do is we say, well, f of x is first. And it's going to get to commit before g, even if g finishes first. F of x then checks all of the preceding, any pages that it's read to make sure they haven't been made stale. If they haven't, it can commit. And then 2 can do the same thing. When g of y goes and writes, if it discovers that some of the pages that it's read have now been invalidated, which it does with some version numbering that's maintained down here as well, it has to roll back. OK? So in the worst case, you get back to serial. But the goal here, again, is to make sure that correctness comes first. Right? We want the program to behave correctly. This is, think of it as an early, unoptimized, pre-generational garbage collector. Right? We want it to be correct. We got 35 years to spend making it run fast. OK? Well, hopefully it won't take that long. OK? Well, if we can just get the TM people to stop working on that, then maybe things will go faster. So, all right, I'm sorry. OK, so there are some other issues to make this run faster. And I'm not going to go into much detail about them. If you have a heap that is essentially just one big heap, and it's a centralized data structure, this completely will not work because one allocation by one thread and one allocation by another will always conflict. So the heaps themselves, the data structure itself needs to be made decentralized. In addition, you don't want memory allocations that are sort of adjacent, like one thread calls malloc, the other thread calls malloc. Everything here is at a page grain. We're using mmap, right? And we're going to be tracking these things on a page level. If they're all intermingled, then you get a lot of false sharing. So what we do is we make sure that every thread has its own set of pages that it allocates from. So if you have two threads and they're allocating stuff, they're not going to conflict because they're all on distinct pages. We do something very, very simple with the GNU linker. Allows us to relocate whole sections of where things end up in the image. And so the linker, we basically make the globals page aligned. So there's a page before it and a page after it. And this prevents some false conflicts that arise from code being right next to globals. Now, you can be in a situation where you have false sharing because two globals are next to each other in memory, and there's an update to one and an update to the other by another thread. We have ways of dealing with that, but I'm not going to go into it. Crucially, we have to deal with I/O. So I mentioned that the idea here is basically optimistic concurrency, but optimistic concurrency means you're going to roll things back. And as we know, it's hard to roll back certain operations. So Morris Hurley's favorite example is launching the missile, right? You launch a missile. Morris clearly is a child of the Cold War. So you have this missile that you launch, and you say, oops, X was 2. That means Russia's not attacking, or whoever our enemy of the year is. And it's too late. Darn, right? So what we do, first, there's a very straightforward, easy thing to do for certain operations, which is to buffer. Right? But there are some things that are just out and out irrevocable. So for example, if you have a network connection, right? So I want to initiate a connection to some remote server and get a response. I can't buffer that, right? I need that response, right? So I really, really do need to execute it. So what do we do? So the trick here, all we have to do is we take advantage of the ordering. So we know, for example, if we have no predecessors, that we are going to commit our state. So whenever we get to an irrevocable point, we say, hey, are there any predecessor threads that are supposed to commit before me? No. OK, is all my state completely clean? Yes, I can go, because I know I'm not going to roll back. I'm guaranteed to commit. All right, so that allows us to actually handle all of this sort of arbitrary I/O difficulty, even though we're doing speculation. OK, yeah?
Guarantee the order with respect to exceptions, like if one thread throws an exception and another thread tries to commit after that, or I mean, so at that time, do you guarantee that when I see the exception, it's as though it was sequentially executed?
So if an exception happens right now, the exception, and it's not caught, or I'm trying to understand exactly the scenario that you're concerned with.
So I mean, if I'm debugging this program, let's say, right, and I introduce some other non-concurrency error, let's say memory error or something like that.
Okay.
And I see a segmentation fault.
Okay.
Would the same? I mean, if you were to run this sequentially, you would see it at a certain point, right? And with Grace, would you end up seeing the same state at the point where the exception is thrown?
Okay. So let's be careful to distinguish exception being thrown from segmentation violation, right? Because one's a programming language construct, and the other is the result of something happening below the PL, right? So like dereferencing null or something, right? Okay, so we could talk about the former, but the latter case, what will happen is the thread will detect it. Currently, the way Grace works is it actually uses segmentation violations as a read and write barrier. So the very first time you read a page and the very first time you write a page, you take segmentation violations, so you know which pages you've read and written, and after that, the pages are unprotected. If you take a subsequent segmentation violation, then Grace will say, wait a minute, you actually had a program error, and it will abort that thread, which is actually a process. So weirdly, it won't take down the program, it'll just take down the thread. So it actually is arguably better than sequential in this case, in that the program will actually survive. So if you have a thread, imagine you spawn a thread and the thread immediately dereferences null. It will be as if that thread had no effect, right? Because none of its changes will ever get committed.
But at that point where you
changing your semantics?
Yeah, it's an interesting question. Yeah. So we thought about this. And we said, do we want to enforce the semantics where when bad things happen, we just abort everything or not? And it's a flag. It's trivial. We basically either say, we have died, and you send a signal to your parent. You basically return in Unix terms, you return -1 instead of 0. It discovers that something bad has happened, and everybody fails. Or you just fail silently. And this is really a policy decision.
Won't you necessarily get the same segmentation violation as sequential execution?
Yes, absolutely.
So I understand the issue.
I think that Kartik is concerned about repeatability or preserving the semantics of execution. And I think it's an interesting question only, well, not only, but especially to me, in this issue of if I've got code and it has some sort of an error, what do I want to do about it? And in sequential case, the normal thing is you crash, right? And if you have a multi-threaded case, the same thing happens. Something bad happens, but it happens at an undetermined time. It would be easy to tell, like I said, the current runtime system actually behaves more nicely, but it's literally a matter of saying return 0 or return -1. Yeah?
I don't see the nicely part of your comment before about the negative effect of turning deadlock into live lock. I mean, silently skipping it seems worse than failing.
Okay, so it's not turning deadlock into live lock, right? Okay.
In the sense that you're taking, because deadlock, your machine's frozen.
Yeah, absolutely.
So now you're taking something where you would have known it crashed, now you don't know it crashes.
Right. So,
I'm surprised that you're being so willing to let it be a policy decision and not want, since you seem to not want that.
I'm sure it has to do with performance.
No, it does not have to do with performance. No, I mean, actually, I thought that this was, I think that this is a philosophical argument. I guess I could put on my Martin Reinhardt hat here and say, if you have a code and the code is going to abort, what do you want to do? Do you want the code to abort, or do you want it to try to continue to execute? And it depends, right? This is one of those classic situations where in some cases, you really want fail-stop behavior, and in other cases, you don't.
I understand that. I'm surprised to see you being willing to be so flexible.
I'm so cavalier. Yeah, I mean, we can be as anal as we want, and we can crash all the time, and that's not a problem. Okay, it's not really something that I focused on, but Kartik asked this question. So, okay, some results. The results here are mostly to show you that this is promising. There's some surprising results. They were certainly surprising to me. So let me explain this graph. This graph was meant to see what the overhead was of using processes instead of using threads. So we wrote a very simple benchmark where the code just, it spawns a bunch of threads. The threads do some work. It's running on an 8-core machine, and so basically, and it spawns 8 threads. Okay. So the top line, which is pthreads, everything is normalized to pthreads. So here, this means that Grace is performing better than threads. It's running in less time. Okay. And as the granularity increases, this is on a log scale, right? Yeah. Bear with me. So as the granularity increases, gradually, Grace eventually sort of asymptotes out. As you can, it makes sense, right? You've got a process and a thread. You would think, as I thought, that, well, there's the initial penalty of spawning a process because you shoot down the TLB, you have to copy file handles, you have stuff that you have to do, and then as the thread gets longer and longer, it would be amortized. Only that's not what happens. Okay? What happens is that for short-lived threads, you actually got better performance. And it came basically, this doesn't happen if you do 1 thread at a time, but it happens when you do 8 threads. All right? So my student came and gave me this graph, which, as you can imagine, I expected this bar to be up there and not down here. And I said, all right, I've done this to the students several times now, and I really need to start learning. I said, you did something wrong. Go find out what you did wrong and fix it. Right? Like you got the graph axes backwards or something. And he ran it again. He got the exact same results. And I said, all right, let's try this. I'll run it myself. So ran the code and got the exact same results. And I said, OK, something is very, very wrong, right? It's like I'm on candid camera. Something weird is happening. So it turns out we did everything. We said, all right, let's look at the performance counters. Let's see what the hell's going on. Eventually, my student, who's very, very good in the Linux kernel, dove into the kernel to see what the hell was happening. And so it turns out that it's actually the Linux kernel that's doing it. But I spoke to a distinguished engineer at Sun, and Solaris does the same thing. So I feel like, all right, it's not just an artifact of 14-year-olds writing code. Okay? And the problem here, this is the idea. Linux has this intelligent thing that it does when you spawn threads. If you spawn threads and you don't say that there's a specific CPU that they have affinity to, then it keeps it on the same CPU where it was spawned for some period of time. The idea is, the cache is all warmed up. It's a thread. It shares the same address space. Let's optimize for that case. And then as the thread runs for longer, we'll load balance it off. All right? With processes don't share address space. They should be distributed immediately. So in fact, this actually works in our favor because the processes are immediately load balanced. They're spewed across all available cores as fast as possible. And so that's why we get a speed up. So I'm certainly not advertising this as some technique to improve the speed of your programs. It was intended to just measure what the overhead was of using these processes. And it turns out that there really is, effectively, because of this artifact, not even no overhead. It's negative overhead, which is not bad. Yes?
Most forkjoin parallelism systems will have some set of worker threads whose startup time is amortized once.
Absolutely, absolutely. So if you think,
how low
that's
would
right.
that be on this graph?
So I mean, if you were to use Silk, right? So these threads, I mean, it would basically be, consider the situation out here at the extreme edge, right, where the thread has been running for a long time. Here, it's a second, right? All of the startup overhead is gone. Everything has been load balanced out. This is the standard sort of, kernel threads that are sitting here with their own decks, right? And so, you end up at the same place, and here the axes are coincident. So I think that's where you'd be. Okay?
Quite a bit lower at 1 millisecond.
So, I mean, at 1 millisecond, I think that it would be, it might be around, I don't know. I mean, right here, the processes are faster because they're load balanced. I would expect it to be about the same, right? That the gap would go away. If they're already running if they've already been running a long time, then they're already been load balanced out, right? So they're all spread out.
Yeah, but you're measuring the overhead of actually forking, right? I think what Dave is asking is that if you have these worker threads sitting around, the overhead of starting new threads is actually
absolutely.
So you still have the whole
right.
cost of starting up a new.
That's right. That's right. And well, I can talk about this some more when I get to some of the other results, because I'm going to talk a little bit about Silk. But you're absolutely right. I mean, if you think of a framework like Silk, or essentially its follow-on, which is the Intel thread building blocks, the idea is you have some set of kernel threads, and then thread spawns are really very, very lightweight continuations. So there's no OS involvement at all. So they're quite cheap. And the goal there was to optimize fine-grained thread behavior. OK, so that said, all the issues of process creation and stuff, with the exception of very, very fine-grained stuff, which I can talk about in a minute, are really not the overheads of Grace. The overhead of Grace is about rollback. And so we wrote a little micro benchmark that just simulates the effect of different rollback rates. And as the rollback rates increase, unsurprisingly, performance declines. The ideal is 8. The dotted line here is with pthreads, which of course never roll back. And then here you get Grace. So as rollbacks increase, you eventually start heading more and more serial. The good news is that you can withstand some number, some percentage of rollback rate and still get reasonable speed up. But all of the steps that we take to eliminate false sharing are really crucial. And if you have true sharing, of course, it's not a good situation. Yes?
So what are you comparing here? This is apples to oranges, right?
It is apples to oranges in this sense. Here, it's the exact same program. Okay? One of them is using pthreads. We're using locks to modify some shared data.
Oh, you are using
Yes, yes. And so Grace ignores the locks and just treats the thing as sort of a transaction.
So they are computing the same thing?
They are.
Like the pthreads just blindly?
No. It's the exact same program. Absolutely. Yeah. In both cases, these are the same programs. Just one is linked with pthreads, one's linked with Grace. OK. So, right. So here's my disclaimer. These are the benchmarks that we're using. It turns out that it's actually quite hard to find benchmarks that exclusively rely on forkjoin. A lot of the classic, also crappy benchmarks, like Splash, rely on barriers. And barriers, while they are conceptually at a high level like forkjoin, they actually break up the threads. So it doesn't make sense for them to be, if you think about it, you've got thread 1 and thread 2, and they have a barrier. They join, and then you have the next threads. If they had been spawn 2 threads, wait for them, spawn 2 threads, wait for them, that would be a perfect fit for Grace. But with the barrier breaking them up, the sequential composability thing doesn't work. Right? So these are drawn from 2 sources. Mostly they're from a suite of benchmarks called Phoenix, which are they're benchmarks that are used to test MapReduce, a shared memory version of MapReduce. Matmul here is from Silk. It turned out that Matmul was the only one of the Silk benchmarks that scaled at all with pthreads, because the Silk benchmarks are designed to stress super, super fine-grained thread creation. So we subsequently came up with a clever hack that allows Grace to run very well even for those, but I'm not going to present those results. So the blue bars here are pthreads. The red bars are Grace. These are speedups on an 8-core machine. You can see that in some cases you get superlinear speedups, and these are cache effects. The good thing to see, of course, this is a little bit surprising. And the reason this happens basically is that lock overhead goes away with Grace. So if the memory spaces don't conflict and you have no rollback, and you also have turned the locks into no-ops, then you get a performance benefit, which is nice. Not what we would expect in practice. So the speedups are good. I have to note, though, we had to make some minor modifications to these programs. The bulk of the modifications, that's the mods that we had to make to most of them, were this particular issue, which is, as I described before, Grace serializes the way pthreads appear in the code. But if you do this, spawn a thread, update a global variable, then spawn a thread and update a global variable, Grace will say, oh, I have to do the whole thread execution first, and then do the update of the global variable. Then I can spawn more threads. So it serializes all the thread spawns. So that was a real killer. So all we did is we hoisted that out of the loop. So we put these all in an array, spawned everything into an array. They each had separate result fields or something, and everything worked out fine. So that was the most important thing. If we extended the pthreads API with, create multiple threads, then that problem would go away. OK, so here k-means is kind of an interesting case. K-means has a benign race. So k-means the well-known clustering algorithm. It has a benign race where it throws stuff. It basically is counting how many things belong to a particular cluster. It converges. So the race is not really a problem. And it's just a number, so it's an atomic value. But for us, this is a killer because Grace sees these things and doesn't know how to distinguish a benign from a malignant race and sequentializes everything. OK.
Could you solve that in the same way by just, instead of putting all the values in the same place, to put them in an array? And
Yeah. So that's right. So one of the things, we just decided, for our purposes, we said we're not going to make pervasive modifications to these codes. Clearly, we could have changed k-means to avoid this problem. Right? But I said, well, let's see what we can do with local changes where we barely understand what the program is doing. OK? And that was really the goal. So in fact, one of my students was like, I think we can fix k-means by doing X, Y, and Z. And I said, no. Right? That's not the object here. The object here is to come up with minimal changes. And in fact, what we're doing now is we're trying to come up with ways of avoiding even making those minimal changes. Right? So the goal here would be you don't change your code at all, and it still performs well. Right? OK. All right. So that's the benign race. All right. That's basically it. So Grace, I think, again, this is really about this sort of idea of garbage collection for concurrency in a way. Right? I want to get rid of all of these errors, just like I used to get rid of dangling pointer errors with garbage collection. And that turns out to be a big win for a number of reasons. Getting rid of sequential errors, it may be more costly than running to the bare metal all the time. There are going to be different ways of programming, potentially. But it seems like a laudable goal. These are promising initial results. Right? So if you use a cleverly tailored algorithm to implement this kind of GC for concurrency, then you actually can get pretty good performance. I should note, this is sort of transactions. Right? But there's no overhead on the main line. Right? So you have these very coarse-grained transactions. There's no logging. There's no compiler involvement. There's no read barriers beyond the initial, have I read this page once? And all of that overhead is amortized. So that's how you get this performance. And there's hopeful Wally. Yeah, happy to take more questions. Manuel.
This is very nice. One criticism I would lob against your benchmarks is that you're starting with benchmarks that are already parallelised.
So this is a story about
arguing that
multi-threaded code.
We're going to make everybody be able to use threads and so on. So I would have to start really with a sequential program and start putting spawns and sinks into places, right?
That's right.
And now the question is, will that do anything?
Yeah, I mean, I think there are deep problems, right, with writing concurrent code beyond just the errors, right? So getting it right is hard enough, but getting it to scale is a whole other question. So this is one of the reasons why I personally remain skeptical of the sort of vision of automatic parallelization, is that it's very, very difficult. It boils down to algorithm design, right? Automatic algorithm synthesis, right? So, I'm going to take, you go ahead and you write your sequential, random sort algorithm that works like this. Randomly permute everything and see if it's sorted, okay? I will discover that that's inefficient, and I'll turn that into quicksort. To me, it's tantamount to this sort of, you start with a sequential program, I'll generate a parallel program that scales. And so, given that seems very, very far off, if it's even possible at all, I figure start with a concurrent program. But the concurrency here is you spawn stuff. But you're still required. The bad part here is there's an additional requirement, which is not only do the data structures largely have to be distinct, they actually have to be distinct at sort of page level grain, which is a drawback of this particular implementation. But in the end, you have to break up data sharing. I mean, that's part of the whole goal. The especially bad part about this, though, is that one conflict can cause an entire rollback, and that's actually something that we're working on. I'd be happy to talk to you offline about this. Yeah, Kartik.
So you started off by listing all the problems in concurrent programs.
Yes.
Like base conditions.
Maybe not all.
Well, okay, a lot of them. So do you have any data? And you look at the class of programs that use forkjoin parallelism.
Yes.
Right? So do you have any data on what frequency of these errors occur in this class of programs?
That's a good question. So I don't have data. I have anecdotal evidence. So the Silk folks have been working on this for a very long time, right? So Silk is a forkjoin model of parallelism. And they have written, I think, 3 different race detectors. And in one of the papers where they talk about it, they call it the non-determinator. And one of the non-determinator papers, they say, they gave all these programs to a bunch of programming assignments to a bunch of MIT undergrads. And almost all of them had race conditions. So that to me is suggestive that it's not much easier, given that MIT undergrads as a whole, not too bad. So, Dave.
As someone who worked on STM, the most surprising and astounding thing is that you can get these sort of results at page-level granularity of fault sharing.
Yeah.
I remember reading the paper. Did you do something in MatrixMultiply to make sure there were, it's like a block matrix multiply?
Yeah. So the one change that we did in MatrixMatrixMultiply, which is, I guess, the most pervasive change, was the base case for the MatrixMatrixMultiply was some arbitrarily chosen number that turns out actually, so it was like, I forget, 16 by 16 or 32 by 32. And we initially figured that as being a potential scalability problem because, it's very, very fine. But in fact, it turns out to have been tuned for a particular cache configuration. So we made it bigger, and making it bigger actually improved the pthreads-based code, but it also helped us because it meant that the blocks were, it was basically 4K by 4K or something. The result was that you were accessing things in page-size chunks at the base. And the way that the memory allocator works is the memory allocator, when you allocate a large object, it guarantees that it starts on a page boundary. So it makes the math very easy. So you know for sure this starts at a page, So I know that this index range to this index range always lies on a page.
A little bit of knowledge about, I'd like to make things like a page size to seep into the code. You do all that.
That's right. I mean, the real problem with things like MatrixMatrixMultiply is that you're dealing with arrays. And you have very limited freedom to move arrays around. With other objects, we actually have a lot of leverage. So one of the things we can do, so we have a prototype that does this right now. You run your program, it detects false sharing, and then it says, here's where the false sharing happened. So with globals, this basically means, oh, add some padding. With heap objects, it means segregate things from different call sites, for example.
About doing it retroactively in garbage collected languages?
Doing what?
Moving things that cause false sharing.
Yeah, we have. Although, I'm not sure if you're on my schedule, but yeah, we. I think this is certainly, there's nothing that precludes this from being incorporated in a GC language, and GC gives you extra advantages as you describe. And there's the ability to move objects around, to sort of shuffle them out or say, this is conflicting and then let's tease those apart, would make things tremendously easier. So we're in a worse situation because we're in C and C++ than we would be if we could actually move things. Yeah, Christian.
Just if I understand it correctly, suppose that you have a binary tree where the leaves of the tree happen to sit in different pages, and then you're marching down the tree and you're spawning threads with every internal node. And as you're getting to the bottom, at that point you update the leaf nodes.
Okay.
In that situation, are you going to do, if there are n leaf nodes, are you going to do n or 2n commits? That is, do you commit with every level up the tree as well?
So let's see. So if I spawn, I'm trying to think of exactly what you're asking. I mean, the commits are directly related to the number of threads and when they spawn a thread. So when you spawn a thread, that's a commit point. And when a thread ends, that's a commit point.
Okay, so 2.
Yeah. Yes?
So most of the benchmark from Phoenix, right?
Yes.
Could you compare the number of line if we're using MapReduce or if we're using Grace?
That's an interesting question. So I spoke to Christos about this. It turns out that using their MapReduce implementation mostly impairs performance. And the number of lines of code is not materially different. It's actually often larger for MapReduce. It's not really a great story for MapReduce on shared memory. I mean, the idea, of course, is, well, this will make it easier to write programs. I mean, I corresponded with him. He basically thinks it's easier for software engineering reasons, and it makes it easier to reason about the concurrency. But the performance story is not that great. So in fact, I didn't include any of the Phoenix MapReduce-based versions for comparison because it seemed unfair, because they're all worse than the pthreads version. And pthreads, to me, are the gold standard. Yes?
So this is a good solution when you have mostly coarse-grained parallelism, right? Yeah. But how do you kind of extend this because a lot of benchmarks are more amenable to fine-grained parallelism?
Right. So that's an excellent question. And I mentioned I was going to get back to this, so now I will. One of the things that we encountered when we tried to do this is I basically had a student change all the Silk benchmarks to use pthreads. Okay? It wasn't that hard. It's mostly mechanical. You see, every place is the spawn, turns into pthread create, and then you have to, save the result somewhere. That's about it, right? And the sinks become pthread joins. Okay? And then we ran them, and none of them scaled at all, except for MatrixMatrixMultiply. And when I say didn't scale, I don't mean with Grace. I mean they didn't scale with pthreads because they were so coarse. Okay? So then I couldn't include them, and I was like, damn, this sucks, right? This is a disaster. Well, it turns out we can run them now. And the way that we run them is through, again, either devilishly clever application of genius or a crappy hack. It depends on the eye of the beholder. The insight basically is this. If you're doing nested, this nested fork join, sort of nested divide and conquer, which is the way Silk works, that means that you spawn a thread, you spawn another thread, they spawn threads, they spawn threads, they spawn threads, right? So we reasoned, once you spawn enough threads, and the number of threads exceeds the number of cores by enough, just don't spawn anymore. Just run the stuff. So we use the nesting depth, and we say, all right, 2 to the nesting depth. Once 2 to the nesting depth is greater than twice the number of cores, we don't spawn anything else. You just run the function. And that means now we can run for small versions, even things like fib. We actually scale now, and you can run almost as fast as Silk, because at some point there's no overhead. Now, this doesn't work if there's load imbalance, right? If there's extreme load imbalance, so that one of the cores, has all the work and all the others are idle, in Silk that gets resolved because of work stealing. For us, it would not get resolved. There are possible approaches that we've not implemented. One, we could detect when this is happening and roll back to the spawn point and then really spawn things. Or you could learn for subsequent invocations not to do that. Yeah?
You have another overhead, right? You have to commit your speculative state. And if you are doing this at a very fine granularity, then your page level smart schemes, they won't work anymore.
OK, so I'm not sure what you're asking. When you say fine grain, I think fine grain means short-lived threads. But are you saying something else?
Threads or tasks, different people call them different.
Sure.
Right? So let's say a few milliseconds worth of work.
Yeah.
Then you have to commit your speculative state. Right?
OK, so if you write a program that does this, right, spawn 8 threads, wait for them, spawn 8 threads, wait for them, spawn 8 threads, and those 8 threads do hardly anything, then the approach I just described will not work. But if you do recursive divide and conquer, where you say, I'm going to carve this big space into half, and then half, and then half, and then the leaves are very, very fine-grained computation, what we do is we turn that whole sort of forest below a certain point, the tree rooted right here, into one big task. And so it works great.
But there's an underlying assumption that the data associated with that tree is contiguous and disjoint from the
disjoint. Contiguous, not required.
Okay.
That's right. And that the potentially conflicting pieces are disjoint. Right. Yeah. And if that doesn't happen, then it's a problem. And, that's a threat. There's a tension between how long you make these threads last and what the likelihood of rollback is. So one of the things that we've done that's not in this paper is we've implemented checkpointing. And the checkpointing is even more crazy, because what we do is we basically, here's the very bad case that we didn't want to have screw us. Do a whole bunch of work, update a global variable at the end. OK? Right? And then, oops, we have a conflict, roll back, waste the whole computation. Right? We do not want to do that. So we have a way around it. And the way it works is we periodically take a checkpoint by calling fork again. And we leave that forked child as a sort of placeholder sitting there. So we fork, we fork, we fork. We get to a certain point, and we discover a conflict. We roll back to the last fork, and the fork is reawakened. If we successfully commit, we just kill all those children. So, yeah.
So what made GC successful, I think, is that first we had the model which said, OK, forget delete. Delete is a no-op.
Right.
And we have infinite memory.
Yes.
That's your model, and now we can work on all these collection outcomes, right?
Yeah.
Now, in this work, again, you spend most of the talk about the technique, how to implement it, but at the beginning, what's the model? So your model is, well, all these things are no-ops, spawn, sync, and so on, and sequential semantics. Is that the right model that will enable sort of the same kind of research that happened in GC to actually succeed, or do we still need to tweak that model a little bit?
OK, so I'm by no means convinced that this is the end at all. But what we were striving to come up with was, what does it mean for a concurrent program that has bugs to be correct? So for a program that has dangling pointer errors, to make it correct, you turn off delete. Right? And you have this infinite memory abstraction. And so that's very clear, easy to understand, easy to explain, and completely solves the problem. The question of what makes a concurrent program correct seemed to be a difficult one. All right, what is the correct version of a concurrent program? And so this is what we ended up with. We said, let's find something where there's an isomorphism to sequential programming. And that's the correct program. But clearly, this doesn't include all possible forms of concurrency. Right? We've restricted ourselves to forkjoin. And so it's a question whether we want to extend this to include condition variables and signaling, for example. But what is a correct program now that you basically have injected message passing, right? I mean, condition variables are just messages. And the correct version of a message passing program, I'm not sure what that is. So, but it's a great question. certainly one worth discussing over beer. All right, thanks everybody.